Okay, so let's talk about vapor pressure. So we haven't talked about what vapor pressure is yet, so I'm going to define first the word vapor. So we've been talking about gases, and you may often hear the word vapor and gas interchangeably. For a chemist, they don't really mean the same thing. CO2, gaseous CO2 is a gas, whereas gaseous H2O is a vapor. Oops, I meant a gaseous H2O. As long as we're talking at 25 degrees C and 1 atmosphere. So a gas that exists at a temperature and pressure which is normally a liquid or solid. Okay, so you might think, well, okay, how's that possible? Because water is a liquid at room temperature. Well, fundamentally, a vapor is the product of evaporation, right? So whenever you have a gas and some solids at room temperature, they are going to vaporize a little bit. They're going to evaporate a bit and solids may sublime, and they put vapor in the air. So even though at room temperature and pressure water is a liquid, there is always some water vapor in the air that has, these are those high kinetic energy water particles that have evaporated off of the surface of the water. So that's what distinguishes a vapor from a gas. A gas is, oh, all right, well, we're above its boiling point, so it's a gas. So at, 150 degrees C in 1 atmosphere, yeah, water's a gas, right? But at room temperature, water in the air is water vapor. All right. So we talked about evaporation in an open container, right? And now I want to talk about what happens if I put water in a closed-off container. Well, here's what we observe. We observe that the liquid evaporates and the volume drops for a little bit and then suddenly stabilizes. So let's talk about why that happens. Well, at first, what's happening is the water is evaporating. Water starts evaporating just as you would normally expect. Because the only two factors that really affect evaporation are surface area and temperature. Now, doing this whole thought experiment, I'm not changing the temperature at any point. What I'm going to do is I'm just going to let it sit there. Now, I'm going to draw a little graph here. So I'm going to draw this is rate over time. Okay, so the rate of evaporation over time is going to stay constant, right? It just stays exactly the same because I'm not changing the temperature and I'm not changing the surface area. So what can happen is that the water, so just like high kinetic energy water particles can escape from the surface of the liquid, if a water vapor molecule with low kinetic energy collides with the surface of the water, because they're bouncing off the walls and each other, and so one of these vaporized water molecules might strike the surface of the water and stick. If it has low enough kinetic energy, it'll stick. Well, so there's also a rate of condensation. So let's think about what might cause the rate of condensation to go up. Now, yes, there is definitely a temperature dependence. But as I said, stay the same all the time. The only other thing that really affects condensation is how much vapor there is, right? So it is a gas, and it is subject to the gas laws. So what we really mean is we mean how much vapor is crammed into a certain amount of space. What we're really talking about here is moles over volume at some specific temperature. This is the pressure. The pressure, in a sense, for a given temperature is kind of the density, how tightly packed the particles are. So the higher the pressure, the more particles there are in a given volume. Now, we don't actually care very much about, we don't care at all about the pressure of the other gases, just the pressure of the water vapor. So what are we talking about here? We're talking about the partial pressure of the water, right? We're just talking about the partial pressure of the water. Now, so at first, when there's no water vapor in there, then the rate of condensation is 0. There's no water vapor to condense. As time goes on, since the rate of evaporation is the black line is greater than the blue line, the rate of condensation, that means that there's going to more vapor is going to go into the air. As more vapor goes into the air, the partial pressure of the water goes up, meaning there's more moles in a given amount of space, which means that so instead of saying how much vapor, the rate of condensation is based on the partial pressure of the vapor. And so it's going to go up, right? So it starts going up and up and up because more and more vapor is going into the air above the liquid, and so the rate of condensation goes up. It goes up and up and up and up and up and up until what happens? Eventually they equalize. Eventually the rate, the partial pressure of the water, or whatever the vapor is, builds up to a point where the rate of the evaporation is exactly equal to the rate of condensation. So this is why you get an initial loss of the liquid, and then it stabilizes because no more net liquid is evaporating. It is important to know that at this point, you get an equal, so you have water evaporating and coming back onto the surface of the water at the same rate. This is a process, called equilibrium. So the molecules that escape remain trapped in the container. Molecules collide with the surface, are recaptured, and so the two competing processes are happening at the same time. At a certain point, the two rates become equal, and we reach something called equilibrium. Equilibrium is a situation in which two opposing processes, in this case evaporation and condensation, are occurring at exactly the same rate, and there's no net change. It is important to know that particles are still passing from liquid to vapor and vapor to liquid, but they're happening at exactly the same rate. So we, on a macroscopic scale, discern no difference in the system. The vapor pressure, so all of that is necessary simply for you to understand what vapor pressure is. Vapor pressure is the partial pressure of the vapor at the point that equilibrium is established. The only thing that affects, there's two things that affect what the vapor pressure of a substance will be. So, again, let me summarize. When you put a liquid in a container, it will eventually reach the liquid, the evaporation of the liquid will eventually reach equilibrium with the condensation of the vapor. This happens once the vapor reaches a certain partial pressure. That partial pressure at equilibrium is called the vapor pressure. Now, one important thing to understand about vapor pressure. This is how the vapor pressure is defined. However, actually, sorry, I have to say something else before I can go on to that. The vapor pressure is affected by two important things. One, the identity of the substance. The more attraction the particles have, right? If we go back to my graph, the more attraction the particles have to each other, my messy graph here, if the particles have greater attraction, then the new line of condensation would be down here, right? And so my I wouldn't need to have as much vapor or have as high a partial pressure of the vapor to equalize the rate of evaporation. So, greater attraction of particles makes evaporation slower. So, particles that stick together more don't evaporate as quickly. So that's a general thing. Because they don't evaporate as quickly, the necessary amount of vapor required to reach equilibrium is less. So their vapor pressure is lower. So vapor pressure is lower with stronger attraction between the liquid molecules. Right? The other thing that affects it, and conversely, substances with weaker attraction have higher vapor pressures. So let me use this as an example. Water and acetone. Okay, let's just sort of do a little experiment here. Water so acetone is very smelly. Why do you think it might be very smelly? Because there's a lot of acetone vapor reaching your nose. It vaporizes easily. Water doesn't really vaporize that easily. Water sticks together really well. Acetone, so we can conclude that acetone has weaker attraction between the molecules. Therefore, which one has a higher vapor pressure? It's the acetone. Okay, now here's what I need to say my thing about vapor pressure. Just because the vapor pressure is defined based on this situation where the liquid is in a closed container, that does not mean that you cannot talk about what that vapor pressure is for that substance at a given temperature any time. That's like saying you can't tell someone your height while you're sitting down, right? Because you're not currently that tall. You know, I'm 6'1", right? And if I'm sitting down, and I can still say I'm 6'1", which doesn't describe my height at the moment, but it does mean that airplane rides are very uncomfortable for me because there's not very much space, right? It still tells you something. And what vapor pressure really tells you? Vapor pressure is directly related to how quickly the substance evaporates. That's what vapor pressure is all about. So let's think about it in those terms. So acetone has a higher vapor pressure because it evaporates quickly, right? So that's really what vapor pressure is all about. It's about how fast something is evaporating, which brings me to the other thing that affects vapor pressure, which is temperature, right? So temperature, if I increase the temperature, right, what happens to the vapor pressure of a substance? It goes up because it evaporates more quickly. So again, vapor pressure is just a measure of is really just talking about how quickly something evaporates. So, let me say this. There's another word that chemists use that is used differently in common language. The word volatile. We often use the word volatile. People use the word volatile to mean explosive or reactive. In fact, we say someone who's really reactive is volatile. For a chemist, all the word volatile means is evaporates quickly. Or we could say, or has a high vapor pressure, right? So volatile just means has a high vapor pressure. That's really it. So remember, vapor pressure related to how quickly something evaporates.